Right? So let's recapitulate. What is it that we were talking about in the last class? So we understood TF, chi-square and Z. Right? Where is that Z distribution used? When you want to test hypothesis about population means, when the population variance is given. When you use the chi-square distribution, when you want to test hypothesis about the population variance. When you use the F distribution, we want to compare the two population variances. Right? And finally, when you use the T distribution, use the T distribution to test hypothesis about an unknown population mean when the population variance is also unknown. You replace the population variance by the sample variance, right? Okay. Now, that brings us to an important point in our regression model. Essentially, the idea was yi is equal to alpha plus beta xi plus ei. Right? Where condition mean of yi given x is equal to xi is given by alpha plus beta xi. Yeah? And what is ei?
Error term.
But what do you mean by the error term?
It's the difference between whether real data is and what observed in our model.
No, it is the difference between each value of y and the condition mean of y given the particular value of x. So for example, if your y-axis is the heights of children, and your x-axis is the ages of children, right? So suppose you are looking at all 18-year-olds. So alpha plus beta xi gives you the average age of a child of a particular age, right? So for example, if x is equal to 18, then the condition mean of y given x is equal to 18, right, will be alpha plus beta into 18, right? So that is the condition mean. But every 18-year-old doesn't have the same height. So if you take a particular 18-year-old, then the difference between the height of that particular 18-year-old and the average height of all 18-year-olds is what is EI. This is the conditional mean. So this is the average height of people who are 18 years old. This is a particular 18-year-old. This is the gap between the two, EI. Right? And EI is a random variable. Sure? So we must clearly understand what EI is. Yeah? EI is the height, the gap between each individual value of y and the conditional mean of y given x is equal to xi. Right? Now there are two things to consider here. This conditional mean function I have specified is alpha plus beta xi. Right? This is a linear function. If I had said it to be alpha plus beta xi square, it would still have been linear. Why would it still have been linear? Because if on the x-axis instead of x I have x square, I would still get a straight line. Yeah, so I still be a linear function. Because what is really important is linear in parameters. Whereas if I have this function as condition mean of y given x is equal to xi is equal to alpha say xi raised to beta raised to gap, right? Then this is not linear in parameters. This is a non-linear function, right? So what the first assumption I am making is that this function is a linear function. But that's not, I am not really compelled to do that. I am doing it just as a starters. As a general modeling strategy, it can be any kind of a function, right? Okay? I might not even want to specify what kind of a function it is and discover the kind of function that exists from the data, which is called a non-parametric model. If I say there is some function parameterized in some way, then I have a parameterized model, I have a parametric regression. Within the parametric regression, I have a linear regression. Right? So y is equal to alpha plus beta xi. The conditional mean I have said is a linear function of xi. Then I have a linear regression model. I can also have a non-linear regression model. Okay. Similarly, each value of yi is the condition mean of y given x equal to xi plus some random error term ei. So the other thing that I need to specify is the distribution of the error term. It's because that e term is a random variable. So I have to say something about this probability distribution, right? A usual way, a common way to assume is that the error term is normally distributed. So if I assume that the error term is normally distributed, I have the normal linear model. So what I have here is a normal linear model, because this is linear, the condition mean of y given x equal to xi is linear, and the error term is assumed to be normally distributed. If I change the distribution assumption on the error term and say that it need not be normally distributed, it can follow any probability distribution that I might want to specify, apart from the not necessarily always normal, but it can take any general probability distribution. Then I have the general linear model. Okay, so if I allow the error term ei, if I no longer restrict it to be normally distributed, but allow it to take any probability distribution, then I have what is called the general linear model. Right? So so when do I get a normal linear model? When this is linear and this is normally distributed. If I keep this as linear and allow this to take any general formulation, any general probability distribution, then I have a general linear model. If I make this non-linear and keep this normal, then what kind of a model would I have? I have a non-linear normal model.
Because the condition is normal.
Yeah, because the condition mean of y given x equal to x. So there are two bits here, no? Yi is specified by two bits. One is the condition mean function and the other is the error term. Right, so if the condition mean function is linear and the error term is normal, I have the normal linear model. If the condition mean function is linear and the error term can take any distribution that it feels like, I have the general linear model. Right? If the condition mean function is non-linear and the error term is normal, then I have a non-linear normal model. And finally, if I let everything be whatever it is, then I have the non-linear general model. Right? So basically, in general, you would like to look for the last thing. But fortunately, for many cases, the normal linear model and the general linear model suffice to model really a very large number of cases. Right? Now, if you are using the whole approach of these four kinds of models, assume some kind of a functional form for the condition mean of y given x equal to xi. So we assume that we know the functional form. If you assume that, then we are using what is called parametric regressions. Okay, if you assume that there is some functional form which is known, then we are saying that we are doing parametric regression. But if you say we don't even know what the functional form is, we are just going to look at the data and discover from the data what the functional form is. Right? Then we are going to go into non-parametric regressions. Or other kinds of regression models that you will soon learn in your data mining exercise, stochastic vector machines, neural networks and all those kinds of things, where you learn from the data. Right? Okay, so that kind of a thing is what we would do. Right, so first, to recap a little bit. So yi is equal to alpha plus beta xi plus ei. This is the population regression function. What do you call it, the population regression function? What do you call it, the population? Any idea? Because it's supposed to describe the whole population. No? So it's supposed to give me the general relationship between the heights of children and their ages as a universal relationship. Yeah? Therefore it's a population regression function. Sure? Okay. So this doesn't specify necessarily children in my sample. This specifies children all over, right? This is the general relationship between the height of a child at a particular age and the age of the child. Right? So this obviously determines what would alpha be? What would alpha be in this case? If yi is the height of a child of a particular age and xi was that age, what would alpha be?
The base height.
The average height.
The base height.
The base height, right? But what would that mean?
There is no one below that.
Yeah, the heights, those will be heights of newborns, no? right? Alpha will be the average height of newborns because xi will be 0. Right? So if you take kids who are immediately, if you take all the heights of the immediately born, not your newborns, you would get alpha. That's the average height. Sure, because xi would be 0. Sure, xi would be 0. And then what would beta be?
Height above alpha.
Per unit changes.
Yeah, so it tells you how height changes with age. That is beta. No?
So I have a question here. Where we are specifically talking about 18 years old.
No, we're not talking about it. Xi could be any ages, right? If you fix x to be 18 years old, then alpha plus beta, x is equal to 18, would give the average height of an 18-year-old. And individual 18-year-olds will obviously have different heights from the average, which will be captured by the EI. Right? So there will be a distribution of the error term for 18-year-old, there will be a distribution of the error term for 17 years old, there will be a distribution of the error term for 16 years old, there will be a distribution of the error term for 15 years old. Right? So basically you got for each of the years, there will be a distribution of the error terms. Right? So those we will call E0, E1, E2, E3, E4, E5, E6. Right? Because there will be average height of 1-year-olds and the distribution of the weight heights of individual 1-year-olds around that height. Right? And if you pick up any individual from that, then obviously you will get, that would be the realization of that particular error term. So I would suppose the average height of a 3-year-old is say 2 feet. Right? And if you randomly pick up a particular child who is 2.5 feet, then the error term for that will be 0.5, half of it. Right? There is a child who is only 1.5 foot, right? Then the error term for that particular child will be minus 0.5. So the gap will be a random error. Why will it be random error? Because it depends on which kid you pick. Right? Now in your sample you picked up one particular kid, but anybody could have been picked up, no? In your sample from the population. So for each of those years there will be a distribution of the error. Right? There will be E0, E1, E2, E3, E4, so on and so forth. Is this clear? Right? So that is what the error term is. Right? It's not supposed to include everything that we have not controlled for, everything that's not there, etc. Properly understood. Okay? It's supposed to include all those only when we make errors in our model formulation. Right? Okay. So you have here. Okay. So now, so this is the population. Right? I want to estimate alpha and beta. I want to know what alpha and beta are. That's the whole idea, no? I want to know what is alpha and beta. So I take covariance of y with x on both sides. We have done. I'll quickly recapitulate that for you. So covariance of yi with xi is covariance of alpha with xi, right? Covariance of beta xi plus covariance of EI xi. Okay, sure. Okay? Because covariance of y with xi will be covariance of xi with all these terms. Yeah. So what is covariance alpha xi? 0. Why? Alpha is not changing. Alpha doesn't move at all. Right? Okay. If you have to actually formally prove it to me, how will you prove that? Covariance of x and y is summation xi minus x bar yi minus y bar upon n. So covariance of alpha and x will be summation xi minus x bar alpha minus alpha bar upon n, right? Alpha minus alpha bar will be 0 because all alphas are the same, so alpha bar will be equal to each individual value of alpha. Right? Okay. So this is equal to 0. Plus what will be covariance beta xi into xi? Write down that in the formula. Summation beta xi minus beta x bar into xi minus x bar upon n, right? That will be covariance of beta xi with xi. Yeah? This will be what? Summation beta xi minus x bar square upon n, because beta will come out common, is equal to beta summation xi minus x bar square upon n. What is that quantity? Variance. Right? Variance. So I have what the heck it is? Covariance of yi xi is equal to beta variance of xi plus covariance ei xi, right? Now can you tell me what the covariance ei xi? Why will it be 0?
Sum of all the distances of.
No, it is what? Summation ei. So again think of in the 18-year-old's example, think of what is ei and what is xi. What is xi? Suppose there is a kid who is 18 years old. So the value of x is 18 for that. What is ei? The difference between the height of a particular child and the average weight of all 18 years old. That is ei. Does that have anything to do with the fact that the child is 18 years old? Does the gap between the individual height of an 18-year-old and the average height of all 18 years olds, does it have to do with the fact that the child is 18 years old? See, look at it this way. The average weight of a Saint Bernard is 60 kilos. Right? My Saint Bernard weighs 90 kilos. So, the mean gap that EI is 30 kilos. Does it have to do with the fact, does this fact that he is an overweight Saint Bernard, does it have to do with the fact that he is a Saint Bernard or is a particularly gluttonous dog? It has nothing to do with the fact that he is a Saint Bernard, no? Because the fact that he is a Saint Bernard is adjusted in the fact that the average weight of Saint Bernard is 60 kilos. This dog weighs 90 kilos not because he is Saint Bernard but because he just likes to eat and eat and eat.
It depends on the parameters that we are taking into consideration for a distribution.
Yeah.
Because if a dog is going to, like with age also its weight would vary.
Yeah, but we are not bringing age into consideration here, right?
In the Saint Bernard case.
Yeah, but so here we are not bringing age into. So suppose you said, okay, so age would be a good idea. So maybe the height of a dog, the weight of a dog is equal to alpha plus beta, the breed of the dog, plus gamma, the height, the age of the dog, plus EI.
Okay.
So what would EI be? It would be the weight, it would be the difference between this individual weight of this individual dog and the weights of all the Saint Bernards who are the same age.
Yeah.
The average weight of all the Saint Bernards who are the same age. Right? Sure? The average weights of all the Saint Bernards who are the same age. Right, so you can control for age as well. So will the EI then have to do anything with the fact that he is an old dog or he is a Saint Bernard? No, it will have to do with the fact that this particular dog has been chosen. Sure? Right? Like for example, if you looked at all the, suppose an average 18-year-old is 5 feet 7 inches tall and the particular 18-year-old who is 6 feet tall. Now, is the gap, which is about 5 inches, has the gap to do anything with the fact that this kid is 18 years old, or is it to do with the fact that in the sample we chose this particular kid?
That has already been taken care of.
That has already been taken care of. So which would mean that covariance EI xi should be equal to 0. Right? Covariance EI xi has to be equal to 0. Sure? Is this clear? Because EI is the difference between each individual y and the average of all the and the average of all the kids who of average of all the individuals for that characteristic. Sure? Right?
Is there a way to prove this mathematically or is it a lengthy procedure?
No, it just you look at it intuitively, because what is EI? EI is the gap between each individual y and the average of all those y's. So obviously this EI is an outcome of pure chance. It's because that particular individual has been chosen. EI takes that particular value because that particular individual has been chosen. But all those individuals are 18-year-olds, no? So therefore the values are what value EI takes has nothing to do with the fact that this kid is 18 years old. Yeah, like suppose in a class, my students were to tell me that I come late today because I stay in Virar. And I said, look here, everybody still stays in Virar.
Correct.
Right? Then obviously the fact that you come later than average has nothing to do with the fact that you stay in Virar.
Right.
Because everybody else stays in Virar, and the average time taken to come here from Virar is maybe 1.5 hours. It takes you 2 hours, right? So it has nothing to do with the fact that you stay in Virar, but the fact that you just walk, you just come leisurely, right? Sure. So therefore this last part will be 0. Right? So we get something important. So we get something crucially important. What we get is covariance yi xi is beta variance xi. Right? Okay? So what is the formula for beta? इसको क्या करेंगे? बीटा will be what? Right. But this is for the whole population. So what we are saying that the height of a kid depends upon the age of the kid. Beta gives you how the kid's heights increase with their age. Right? For the whole humanity. Right? That is what beta is. But you don't have the whole of humanity. You have a sample. Right? Okay? So you can't know what covariance y xi and what variance xi is for the whole of humanity. You need to estimate it from the sample. So what's the formula that you use for covariance yi xi? So this will be summation xi minus x bar minus yi minus y bar upon n summation. This n will go with this, right? And I will get yeah? Correct, no? This is formula for the variance, the formula for this formula for the covariance, this is formula for the variance. N gaya, na? Now the point is this is not really beta though. Because to get beta I have to get the covariance between y and x for the whole humanity and the variance of x for the entire humanity. Right? Because I am saying that this formula applies to all people in the world. But do I have covariance y xi for the entire humanity? No, I have collected some data on some only 35 people. Right? Okay? Fine. So I have a very, very microcosm of humanity with me. Sure? So therefore, I will not call this beta, but I will call this beta hat. Why? Because it's my guess at beta. Right? It's my guess at beta. Okay? It's my guess at beta. Right? Okay? And I will call this beta hat OLS. I'll tell you why I will call it beta hat OLS. Okay? I'll call it, why I call it beta hat OLS. I'll quickly tell you. So this should be, this is so different from Sunil's neat writing. No? Yeah? Summation exam minus x bar square. Yeah? I try my best to improve.
What is OLS?
I'll tell you why it's called OLS. Okay? Because, okay, now first, so beta. Let's also find out how to find alpha hat. Okay, अपने पास क्या है? yi is equal to alpha plus beta xi plus ei. Right? Expected value of yi is equal to alpha plus beta expected value of xi plus expected value of ei. Right? Now you must tell me what is the expected value of ei. 0. Why? Yeah? Why is the expected value of ei 0? Think of the 18-year-old example. Or think of Marty's example, St. Bernard example.
Whatever deviations that should be around the average must be average out. Has to be then only that average will come.
What he's saying is that what is ei? Ei is the gap between each yi and the average of all the heights for all the 18 years old. Now if I average EI, what will I do? I will take the value, the average value of each yi minus the average value of each yi of yi. If EI is yi minus average of y, if I take average of E, then I will take the average of yi minus the average of yi. Average of the average of yi is just the average of yi. So I will get average of yi minus the average of yi. Basically, if you average out the deviations from an average, they will always be 0. Right? If you average out the deviations from the average, it will always be 0. Right? So expectation EI is 0 for us. Okay. So this becomes 0. So I have okay. So what do I have? I have alpha right? Sure. Now what is expectation y? The average y for the whole humanity. मेरे पास है वो नहीं, मेरे पास क्या है? सैंपल. तो सैंपल में एवरेज ऑफ ऑल ह्यूमैनिटी को मैं किससे रिप्लेस करता हूँ? सैंपल एवरेज से रिप्लेस करता हूँ. तो एक्सपेक्टेशन y becomes y bar. Right? Sure? ये बीटा जो है वो भी मेरे पास नहीं है, वो तो ह्यूमैनिटी का है. लेकिन मेरे पास I've got a snapshot of that, I've got a guess of that, right? That guess is beta hat OLS. And expectation x भी नहीं है. Expectation x is the average across the whole living humanity. I don't have that. So I replace it with whatever average of whatever I have. X bar. So this, because this is estimated, this is estimated, this is also estimated. I call it alpha hat OLS, right? So you know how to get beta hat OLS, alpha hat OLS? Very, very simple. If I give you a sum, will you be able to do that? Covariance x y लेना है, उसको variance of x से divide करना है, beta hat आ गया. Y का average लेना है, minus जो भी beta hat आ गया, उसको x से multiply करके subtract करना है, alpha hat आ गया. Right? So it's not really a big deal to get it. Sure. Okay. Now, let me ask you more questions. Now first let's answer her question. Why is it called OLS? Okay? Why is it called OLS? Now there, थोड़ा सा important चीज होने वाला है. And we're going to learn about how to actually incorporate, how to get the formula for Marty's age as a function of. So Marty's age we are saying is a function of three things. Is a function of the fact that Marty's weight is a function of the fact that he has a particular breed. He's Saint Bernard. And then he has a particular age. And finally that is Marty himself. Right? So there is something, Marty's weight is broken into three parts. Right? One is which breed he is. The second is what is his age. And finally which particular individual he is. Because that gluttony is specifically to Marty, right? Eating everything in, right from cucumbers to Karellas to everything is a Marty interest. So we say that his weight is because of his breed, his age, which are common to all Saint Bernards, and the fact that something specific to Marty.